This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Hey everyone, and welcome to our discussion. Today we're tackling the Bohr model of the atom, a cornerstone of atomic physics. We'll be examining two papers that offer different perspectives on this model, one providing a basic introduction, and the other offering a more interactive approach through simulations. Ready to delve into the quantum world?
Absolutely. The Bohr model, despite its limitations, provides a crucial stepping stone in understanding atomic structure. It's a simplified representation, but it successfully explains key phenomena like the hydrogen spectrum.
So let's start with the basics. The first paper describes the Bohr model as a solar system-like structure with electrons orbiting a central nucleus. What's the significance of this analogy and what are its limitations?
The solar system analogy is helpful for visualization. It highlights the central nucleus and orbiting electrons, illustrating the electrostatic attraction holding the atom together. However, it's crucial to remember that this is a simplification. Electrons don't follow precise, predictable orbits like planets. Quantum mechanics provides a more accurate, albeit more complex, description.
The paper mentions that the Bohr model improved upon earlier models like the plum pudding and Rutherford models. What were the key shortcomings of those earlier models that the Bohr model addressed?
The earlier models couldn't explain the discrete nature of atomic spectra. The plum pudding model, for instance, envisioned a diffuse positive charge with electrons embedded within, failing to account for the distinct spectral lines observed in experiments. Rutherford's model, while correctly identifying the nucleus, couldn't explain why electrons didn't spiral into it due to electromagnetic radiation. Bohr's model introduced quantized energy levels, resolving this issue.
The paper emphasizes the Bohr model's success in explaining the Rydberg formula. Can you explain what the Rydberg formula is and how the Bohr model provided a theoretical basis for it?
The Rydberg formula is an empirical equation that accurately predicts the wavelengths of light emitted by hydrogen atoms. Bohr's model provided a theoretical explanation by postulating that electrons occupy specific energy levels, and transitions between these levels result in the emission or absorption of photons with specific wavelengths, perfectly matching the Rydberg formula's predictions.
The paper also discusses the wave nature of electrons, as described by de Broglie. How does this wave-particle duality fit into the Bohr model?
De Broglie's hypothesis suggests that electrons exhibit wave-like properties. The Bohr model incorporates this by requiring the electron's wavelengths to be an integer multiple of the orbit's circumference, ensuring constructive interference and stable orbits. This condition restricts electrons to specific energy levels.
The first paper mentions that the Bohr model shouldn't be taken as a completely accurate representation of reality. What are its major limitations, and what model superseded it?
The Bohr model worked well for hydrogen but struggles with more complex atoms. It fails to accurately predict the spectra of multi-electron atoms and doesn't account for electron spin or the fine structure of spectral lines. Quantum mechanics, with its wave functions and probability distributions, provides a far more accurate and comprehensive description of atomic structure.
Now let's move on to the second paper. This one focuses on interactive simulations of the Bohr model. What are the advantages of using simulations to learn about atomic structure?
Simulations offer a dynamic and engaging way to visualize abstract concepts. Students can manipulate variables, observe the effects on atomic properties, and gain a deeper intuitive understanding of the model's principles. It's a powerful tool for active learning.
The paper describes a simulation that allows users to switch between a particle and a wave model of the electron. What insights does this feature provide?
Switching between the particle and wave models highlights the wave-particle duality of electrons. In particle mode, you see electrons orbiting the nucleus. In wave mode, you see standing waves representing the electron's probability distribution, emphasizing the quantum mechanical nature of electrons.
The simulation also allows users to adjust the principal quantum number, n. What does this parameter represent, and how does changing it affect the atom's properties?
The principal quantum number, n, determines the electron's energy level and the size of its orbit in the simplified Bohr model. Increasing n increases the electron's energy and moves it to a higher energy level, farther from the nucleus.
The paper mentions that altering the orbit's radius in the wave mode can lead to a non-stationary state. Why is this the case?
In the wave model, only specific radii corresponding to standing waves result in stable states. Altering the radius arbitrarily disrupts the constructive interference pattern, leading to an unstable, non-stationary state where the electron's wave function is not a solution to the Schrödinger equation.
Both papers highlight the importance of understanding the limitations of the Bohr model. Why is it still relevant to study this model despite its limitations?
The Bohr model, despite its limitations, serves as a crucial stepping stone in understanding atomic structure. It introduces fundamental concepts like quantized energy levels and wave-particle duality in a relatively accessible way, providing a foundation for more advanced quantum mechanical models.
So in summary, both papers offer valuable insights into the Bohr model, one providing a theoretical overview and the other a practical, interactive approach. This combination provides a comprehensive understanding of this important model in atomic physics. Thank you for joining this discussion. I hope this exploration of the Bohr model has been insightful for you.